Well, hi everyone, and greetings from Northern Michigan. This is Bob the Science Guy, and Happy New Year to each and every one of you. Today, I want to have a look at a classic misconception of the science denial community, and that is one of inability to appreciate magnitude. Now, this pen, for example, has mass. If I move the pen from here to here, technically, I'm changing the center of gravity of the Earth. And by changing the center of gravity of the Earth, I could probably change its rotation to a very slight degree. However, in the science denial community, the approach is generally, well, if you've moved the pen from here to here, you should be able to demonstrate a change in the rotation of the Earth because you changed the center of gravity. If you can't do it, the Earth isn't rotating. This is a classic misunderstanding of orders of magnitude that you see in the science denial community. Now, while this is obviously a ridiculous example, you see shades of this argument in the arguments of the science denial community and the flat Earth. Now, this is Brian Mullin. He's a structural engineer, which is a sub-branch of civil engineering. He designs bridges and buildings. Now, despite working in this field on a daily basis, Mr. Mullins has come out with a series of videos that completely undermine physics and engineering. And these videos were put out under the title Balls Out Physics. They were flat Earth videos. Now, normally I would have let it go. Somebody got a hold of him and talked some sense into him perhaps, or the universe just worked itself out, and these videos are no longer being made. However, they were copied, and as a result, I've decided that they needed to be addressed. So today we're going to have a look at Mr. Mullins talk about the thermosphere, the ISS, and satellites. So let's cue up the music and get going.
Hi, I'm Brian Mullin. This is Balls Out Physics, Episode 4, the ISS, Satellites, and the Thermosphere. When I first started researching flat Earth theory, one of the first things I had to accept if I was going to even think about the possibility would be that NASA and all of the photographs or composites, as they are actually called, or in video, whatever you want to call it, from space is fake. And I mean, that's a giant leap you have to take to to accept something like this, or to even consider it.
You know, Brian, you're absolutely correct. In order to even consider the idea that the Earth is flat, despite all of the evidence to the contrary, you have to come up with a way to justify in your own mind that all that evidence is wrong and your thoughts, your understanding somehow is correct. So here's the basic problem that you're facing. We have satellites in orbit. We have weather satellites. We have spy satellites. We can see satellites with our naked eye from the ground. I've got photographs of satellites with my telescope. This is overwhelming evidence that there are indeed satellites in space. So your job as an engineer in the flat Earth, or at least as you saw it apparently, is that you had to lend some professional credibility to the idea that maybe all of this is wrong. And you had to give a reason that it could be wrong so that you had plausible deniability when you looked up and you saw the ISS pass overhead. This is not intellectually honest, Mr. Mullin. But let's go ahead and continue.
And so I started watching videos that people had produced showing that the ISS was a hoax, and that satellites were fake. A lot of people, there were videos showing that on spacewalks, when it looked like they're on space, people caught a bubble rising from an astronaut's helmet, or a guy with a scuba tank inside the ISS in a window, and just other things like that.
I think we have to pause right here for just a second. You and I are both professionals. You're an engineer. I'm a physician. In my field, if I were to put out information in my field, I don't think that I would quote the National Enquirer. I don't think that I would watch YouTube videos to find information in my field. I spent years training in school and going through internships and residencies and many years of clinical practice to understand how to do research in medicine. I would assume that you do the same thing in engineering. You don't watch YouTube videos by non-engineers to learn how to do basic engineering principles or understand engineering problems. They may inspire you to think about it, perhaps, in a new way. But that's not where you get your information, especially if you're going to go against engineers, people in your own profession that designed these satellites in the ISS, that built them, that man them. You are going to go out and basically call a fellow professional engineer a liar. You can do that. We can question each other. However, if you do question another engineer, I would suspect that you would have something more than YouTube videos to back it up.
And so I first started seeing that stuff, and it was pretty convincing. But at the same time, I thought, well, it's not definitive proof, because how do I know that this stuff hasn't been edited in to sway opinions? Because there are people out there that believe the Earth is flat, and they want everybody else to believe it too. So I remained skeptical. My opinion started to sway a little bit, but I still was trying to prove it wrong. But I'll never forget the moment that everything clicked. And that was on a Friday night. I was just watching videos, doing my typical thing, just wondering, trying to prove these things wrong that I was seeing. And I don't remember what video it was, but the narrator in the video said, how are there satellites and a space station in the thermosphere layer of the atmosphere when the temperature gets up to 2000 degrees Celsius? And that's when everything clicked. I remembered, oh, wow. I remembered from astronomy, my professor talking about the temperature in the thermosphere. And I remember her taking a marker like this and holding it out, and held it in front of the class like this. And she said, the temperature in the thermosphere layer of the atmosphere is upwards of 2000 degrees Celsius, or can get up to upwards of 2000 degrees Celsius. But you can't actually measure the temperature because the gas particles in the thermosphere are spread so far apart that there are not enough of the particles collide with the tip of the thermometer to make it show a hot temperature.
Well, Brian, right about now is where I see a disconnect occurring. All right. Behind me, you'll see a picture of a glacier. I don't know where it is. I saw plenty of these when I was up in Alaska. Here's a rock. Now, if I were to heat this rock up red hot to the point that it became molten, and I dropped it in the middle of that glacier, would it melt the glacier? It'd melt the area right at that spot, but it wouldn't melt the entire glacier, would it? There's simply no way to put enough heat in this rock, no matter how hot it is, to have enough of a thermodynamic impact on that glacier to melt it. Now, Brian, let's just take a moment and look back at the different ways that you transfer heat from one object to another. You can do it with a contact transfer. I can take my hand and I can put it on the burner of a stove. The hot element of the stove will burn my hand because it's directly in contact with it. The other way that I can do it is that I can let that stove heat up a Dutch oven. And even though the food in that Dutch oven is not in direct contact with the heat, it's got so much heat in the air that the food will cook. That's how a forced air heater works in your house. You warm up air, and that air is then pumped into the house and exchanges with the cooler air in the house, which is returned to the furnace. But it transfers the heat of the furnace by transferring the warm air. The last way is radiant heat. That's how the sun warms the surface of the earth. Even though the sun is very hot, there's no direct connection between the surface of the earth and the sun. And it uses electromagnetic waves to do that. For example, infrared heat. That's how an infrared food warmer works. That's how a microwave oven works. So these should be principles that are well familiar to you, Brian. And I don't understand why, if you've already admitted that in your astronomy class, probably as a freshman, they talked about the heat of the thermosphere and how the individual atoms are very hot, but there are so few of them, they won't even register on a thermometer. So the question now becomes, why are you putting this information out into people that don't understand the transfer of heat as well as you do, or I do for that matter? Is it not designed to cause confusion and doubt, to try and give some plausible deniability to something that is readily evident to your naked eye, such as the ISS passing overhead and the people transmitting from the ISS? Is this ethical, Brian? Here's a pretty good rule of thumb for how I do my job. All right, based on my training and my experience, if you come in with a certain set of symptoms, I think that this is what's going on with you. It's most likely this, to a very high probability. And I know how to treat that. And what I'll do is I'll go ahead and I'll prescribe treatment for you. Now, once I've prescribed treatment for you and you're doing it, I expect you to get better in X number of days. So here's a good example. Say you come in and you hurt your back. It's the first time that you ever hurt your back. If you're a young working person and you did not have an automobile accident, you simply lifted something at work or at home, and you kind of wrenched your back a little bit, the chance of you having a fracture in your back is almost non-existent. Now, if you don't have any symptoms of spinal nerve impingement, you will respond to 3 days worth of rest, non-steroidals, and some warm showers. Okay? So that's what I'll recommend that you do. I'm not going to order a $1,750 MRI of your back on the first episode that you come in with back pain, especially if you have a very good story behind it. If you come back in a week and your back pain is the same or worse, or you have new symptoms, I am required to reassess my original opinion because it's corrective information coming in. I'll have to take additional tests. I'll look for additional things. I'll admit that my initial impression was wrong. So right now, you have a choice to make, Brian, and that is, if you somehow don't believe that space is real, yet we see evidence of objects in space and people in space, like the moon landings and the ISS, you need to reassess your impression about whether or not space is real. You don't sit down and declare that the ISS doesn't exist because you don't believe space exists. Let's go ahead and continue.
And the second law of thermodynamics asserts that energy has quality as well as quantity, and actual processes occur in the direction of decreasing quality of energy. And what that means in terms of heat is that something that's hot will move to a colder area because the energy in something that's hot is higher than the energy in something that is cold.
Now, again, I don't really know what to make of this because nobody's in disagreement with that. If this rock was red hot and I dropped it on that glacier, heat would flow from the rock to the surrounding ice. But the question that we run into is, how much of an effect will the heat from this rock have on that glacier? None. It may make a small puddle, a rock-sized puddle, but it's not going to melt the glacier. It's not even going to be able to burn its way all the way down to the base of the glacier. This rock is going to melt maybe an inch of ice right where it sits. So once again, it's an issue of magnitude. I don't disagree with his principle that heat is energy or that heat goes from hot to cold. The question is, and this is the foundation of his argument, is simply because the thermosphere is hot, there is so little matter in the thermosphere that the transfer of that heat, which is on the individual molecule basis, is going to be insignificant in something as large as a satellite or the ISS. There's just not enough transfer of that heat to those objects. The fact of the matter is that the radiant heat of the sun is going to make far more of a difference than the thermosphere. When the Apollo capsule was going to the moon, one of the things that they talked about was the barbecue roll. And that is that the capsule would rotate once every minute or so to allow one side to kind of heat up and then rotate into the cold of the dark side of the capsule, and let that heat dissipate. On spacecraft, there are also radiators that dissipate internal heat out to the cold of space. These are not difficult principles to understand, and even a cursory look at Wikipedia would tell you the answers. So why are you making videos, Brian? bringing doubt into this when the answer is so readily available to you? Inquiring minds want to know.
And they say, for example, a cup of hot coffee left on a table eventually cools, but a cup of cool coffee in the same room never gets hot by itself. The high temperature of energy of the coffee is degraded. It's transformed into a less useful form at a lower temperature once it's transferred to the surrounding air. So they give a little picture, they show you a picture of this. I mean, you can probably imagine a cup of coffee cooling down.
Dear Lord Brian, yes, of course, a hot cup of coffee left on a table in a cool room will cool. That does follow the law of thermodynamics, and we verify that in our day-to-day life. And you further go on to say that that heat is dissipated into the surroundings. That's exactly how we cool spacecraft. An external source of energy warms the spacecraft up, specifically the sun. We then either rotate the spacecraft or we use radiators for the internal heat of the spacecraft and vent that heat out, so to say, into the surrounding space. When you were in engineering school, you had to have had at least a cursory understanding of how an internal combustion engine worked and how the radiator system worked. So what are you trying to demonstrate here?
Why this all clicked for me, and you may or may not agree with this, is that I don't understand how this heat is not being transferred to the International Space Station and all the satellites up there. And so I drew here the thermosphere on the board, and I chose to say it starts at 100 kilometers because there's other charts out there that show 100, and it's just easier to use 100. And I also said that the top of it is at 600 kilometers because there are other charts that show it at 600. And NASA tells us that the Hubble, Fermi, and Spitzer, Hubble being the most famous telescopes, are around 560 kilometers, and they say that they're in the thermosphere. So that's why I chose 600. And these red dots on the board are supposed to represent the air, the gas particles, which basically the atmosphere up there. Okay, and red because they're hot, and you know, I've also got the ISS and satellites up there, and down here I've got the lowest LEO, which is supposed to be around 160. 160 kilometers, and there's supposed to be thousands of satellites out there. So there's not just one down there, there's multiple, but this is just a representation. Obviously not the scale. I tried to illustrate this, that at the lower temperatures of the thermosphere, the air is going to be more dense. If you see, I've got more dots down here than I do up here because the gas starts to try to expand away from each other because it's hot. The hotter it gets, the more the particles want to get away, okay? But the particles are so far apart where all these satellites are that there's not enough of them colliding with the satellites and the ISS and everything to make them melt. That's basically what my astronomy professor said with the thermometer example, and this is the general accepted excuse or reason for why these satellites aren't melting and why astronauts aren't burning up, and that's it.
Okay, so Brian, here we are. This is your understanding that the thermosphere is very hot, and you acknowledge the fact that there is very little matter in the thermosphere. Now, even though your astronomy course actually addressed this and talked to you about the reasons that the rock won't melt the glacier, you think that they're wrong. So now what you have to do is you have to kind of come to Jesus moment. You either have to come up with something serious as to why they are wrong and show by experiment perhaps why you're right, or two, you have to reassess your own understanding of what's going on, because your understanding says that this cannot work, yet it does work. So your understanding is the flaw here, not the process.
It kind of makes sense. Someone pointed out on my channel, it was made a pretty good comment. He said, well, what if it's like an oven? You know, when an oven's hot, you put your hand in the oven, and your hand doesn't burn up immediately. You can put your hands into the oven because the air is is pretty spread out, but if you keep your hands in there, eventually they will start to cook. Okay. And I thought that was a good example, and it made me really start thinking about this. And I thought, well, if something's hot, to keep it hot with a surrounding cooler environment, you have to keep putting heat into it or energy into it to keep it hot. So going back to the pot example, the pot's on the stove, the lid's rattling around. You say, "Oh, the lid's going to blow off." So you turn the temperature. You just turn the dial off, turn the heat off right away, and usually the lid stops bouncing around pretty quick, and the pot and everything cools down pretty fast because the room temperature air around is so much lower, and that gets into potential difference. The lower the temperature, the more mass around something that's hot, the quicker the temperature can dissipate to the surrounding environment. Okay. So I started thinking about the thermosphere in this sense, and all these red particles, or these gas particles, the red dots representing them. Something's got to keep them hot, right? Because space is supposed to be cold, very cold, because there's nothing out there, and the mesosphere below the thermosphere is also minus 100 degrees Celsius. If you can see down here, I drew a bunch of blue dots and tried to show them very dense because the temperature's cold, so they're closer together. There's gas here, and there's air in the thermosphere represented by these particles, and they're hot, really hot. As you get up to the top, they get around 1,500, 2,500 degrees Celsius, as I've written up here, and they get into the exosphere. The air particles are still hot, but they're very far, they're spread apart, and not enough of them are colliding with the objects that are up there, so that's why we're told that they don't burn up. Well, something's got to be keeping the thermosphere hot. And what is that? Well, obviously it's the sun, because that's what's supposed to warm the earth. But that's also kind of questionable because, the reason that heat isn't transferred to the satellites is because the air particles are too far apart. Well, in space, there's supposed to be no air. How does heat from a sun that's 93 million miles away travel through the vacuum of space to get to Earth and warm the Earth? That was always a big question for me. And it doesn't make a lot of sense, but it is accepted that electromagnetic waves can pass through space or through a vacuum. Okay. And light in astronomy, that term covers the whole electromagnetic spectrum. And to give you an idea from my astronomy book, here's the electromagnetic spectrum up here at the top. And you can see it's made up of visible light, which is the rainbow in the center. And that's a very, very small portion of the spectrum. And then there's ultraviolet, infrared, X-rays, gamma rays, and radio waves, of course. And radio waves need to be able to travel through space for NASA to communicate with the space station, right? Or with the space station and Apollo missions, whatever.
Now, the remainder of Brian's presentation kind of goes along in this same vein. Apparently, Brian doesn't know how a microwave oven works. That is electromagnetic radiation, light, that transfers energy from the microwave source to your food. Causes the water molecules to vibrate, and that's what heats up your food. That's a transfer of energy at a distance. Radio waves do work in space, obviously. That's how GPS works, right? Now, I'm sorry that you apparently slept through your thermodynamics courses and your heat transfer courses, because this is really 8th grade stuff that you're messing up right now. I don't think that we have anything else to gain by watching you humiliate yourself any further, Brian. Here in Michigan, we have a rule in football. If one team is ahead of the other by 57 points or something at halftime, they call the game then. It's called the mercy rule. And I'm going to invoke the mercy rule with you right now, Brian, and I'm not going to continue this video. You have demonstrated that you have absolutely no concept of how heat transfers. You have no concept of magnitude as far as how much one molecule of air per cubic meter will actually warm a piece of aluminum in orbit. I don't think that there's anything more to gain by continuing this other than to dismiss your argument for the reasons I've already given as ridiculous. So, this is Bob the Science Guy signing out from Northern Michigan. Happy New Year, and thank you very much for your support of the channel. We've got some exciting things coming in the future. 2022 is going to be the year of the Astrolabe. So, see you then.